So I'm happy to introduce Muriel Livernet to talk about multicomplexes and spectral sequences on homotopy multiplication.
Thank you. So first, I would like to thank the organizers for giving me the opportunity to talk here and well, to have this perfect weather in Belfast and all this amazing presentation that we had so far. So there's a bunch of collaborators here, but I want to mention two other persons that are not here, which is Constance Rotain, because the first story about this was a paper by Constance and Sarah about derived infinity algebras, and I said, when I read this, I said, oh, but there are operads underlying this. And then I kind of said, oh, I'm confused that there are resolutions of operads. So I talked about operad and now that this is done. Okay, so this is the operad part. And also on this derived infinity algebra, we had our first woman in topology with Marcy in our group. And we worked also with derived infinity algebras. So for this, there were some ideas, and ideas are vertical bicomplexes and twisted complexes that I will talk about during. So it's a joint work with Sarah Whitehouse, but with many co-authors, mostly issued from the Women in Topology workshops, but then with, gone work on these topics. So also my main domain, this is a connection with operads and calculus. Of course, operads are always there to my mind, and calculus, I love calculus. And so don't be afraid, there will be a lot of formulas, but just because for me, it's a way to see how objects work. So you don't need to read them. It just, for me, it's like diagrams. I feel more free with formulas than with other stuff. So I hope I tried something. Okay, so you see the light here? No, I think, yeah. Yes. Also, don't be afraid by the number of slides that you see, because I'm pretty sure that I won't go to the end of the slides. And I just want to explain you things, and things are, my aim here is to say that you listen to me and you say, oh, that rings a bell. Oh, I have seen this computation somewhere. Oh, it's connected to the work I've done. And then I love the spectral sequences, and especially computing spectral sequences. So then you can come and ask me some questions. But everything is pure linear algebra. So I don't go out of linear algebra, a little bit of homotopical algebra, and that's it. Is it no, it's already, okay. So spectral sequence for me is quick and simple, okay? It's just a family of complexes. So I'm over a ring, any ring, commutative with unit, of course. And so I have a bunches of complexes, AR for each R, okay? And there's a connection between the next complex and the homology of the previous one. So you see that I drew the arrow between the homology of AR and AR plus 1 in the wrong sense, because usually you say, oh, okay, I'm computing the homology of AR, and I have an isomorphism with the next page. And if I have time, I will explain why I put this arrow, but because it's an isomorphism, you can you can work with the arrows the other way around. And the morphism of spectral sequences is just, you have a bunches of maps of complexes, and it must commute with this characteristic. And there's a category, the category of spectral sequences. Okay, so this is the easy definition. Of course, if you have occurred some spectral sequences, usually it's bigraded, vibrated. Sorry. And in practice, so I will work only in the unbounded case, always. Okay, all what I will say is unbounded. And you have different choice of by degree for your DR. So I tried to count the number of choices you have because, I mean, there are many conventions. So here you have 8 choices. But then I said, oh, yes, but it's 8 choices if you think that your first differential is vertical. But then it can be horizontal. So indeed, you have 16 choices. So we don't care. You pick your favorite choice. Today, the choice is that I have TR of by degree minus R minus 1. So in some sense, everything is homologically graded. So D0 goes down, D1 on the left, D2, well, you see the picture, okay? And the total degree is the sum of the by degree, and it's gives you a differential of total degree minus. So this category is additive, but it's not complete nor complete. We have counterexample of maps that have no kernels, no co-kernels. So, but we still want to do some homotopy theory, okay? So by homotopy theory here, I'm interested in, I have a map from 2 spectral sequences, and of course this map, you start at page 0, but then it induces a map at page 1 and page 2 and so on. It's completely determined by the first page of the spectral sequence. And then you ask that at the R page, your map is a quasi-isomorphism. So, I mean, this is equivalent in the world of spectral sequence to ask that after page R, they are all isomorphic. And it's a way to compare spectral sequences. Okay. Now I have my weak equivalencies, so I fix an R, which is important. And that from page R, it's after R, it's isomorphism. And so this relative category of this class of weak equivalencies is stable, contains all isomorphism, as the 2 out of 3 property, stable on the retract. So, I mean, you can imagine that you would like to do some a little bit more like infinity category setting, or where I'm more at ease is a model category structure. Okay. However, I already told that spectral sequence has no limits, no co-limits. So, well, model category structure is a bit strange, okay? And especially, I mean, for instance, we have an idea of what would be vibration here, but then it's not stable under pullback. So it's really badly behaved. But there's a lot of other categories. So here is the big picture I want to explain. So it's a big picture, and again, don't be afraid, there's lots of things, but I try to explain you. So how you usually build your spectral sequence. So, I mean, there are some different schools. The schools with exact couples and the school with filtered complexes, which for me is more linearly, well, it's more easy to have some calculation, but of course, if you have a filtered complex, you can build an exact couple and then a spectral. So there's something missing here is exact couple, because I'm not considering exact couple in the theory. So filtered complexes, you have a spectral sequence associated to filtered complexes. What I want to tell you about is multicomplexes and twisted complexes, which MC and TC, well, you can read. And there are truncated version of multicomplexes, the big M, and then I will focus on example with 2 and 4 at some point, okay? And so the idea is that, of course, it's a survey of some results that we had with Sarah and the other Carter for the last 10 years, almost. So it just, so in black, I will try to give this survey. I will definitely talk about the 4 multi-complex. The multi-complex is truncated at 4. I have prepared thing for extended spectral sequence, but I'm not sure I will be able to talk about it. And directed graph is something we have started with Sarah and Emily Roth, but I will not have time to talk about it. So next conference, I hope that I will have more to say about directed graphs. Okay. So what is the idea is that, of course, you have this functors that relates all the category inside to a spectral sequence. And what I would like to do is that you have a functor from a specific category to spectral sequence, and then I can pull back the weak equivalence through these functors and define my ER in every category there that has a functor from C to spectral sequence to be the weak equivalents that are sent to ER in spectral sequence. And now, what is the big plan? Do we have a model category structure with ER on these different things? So maybe these different categories have limits and colimits, and then I can hope to have a model category structure. What I know to do is to produce some coefficiently generated model category structure. So that's why this question is there. And then you have a fixed R, as I said, HR will provide with a model category structure. So I want comparison of this big picture when R is fixed, or inside a category, I would like a comparison when R varies. So that are the kind of questions that we have. Okay, so before that, I just want to review the model category structure on chain complexes. And so this is a projective model category of unbounded chain complexes. And then I will tell you a little bit about how do we provide a model category structure on filtered complexes from the same IDs. Okay, so we know that it admits a coefficiently generated category with weak equivalents are quasi-isomorphism, and fibrations are maps that are surjective everywhere. Okay, when it's bounded, then you need to relax this condition of surjectivity, at least at the first degree. But here, because it's unbounded, it's surjective everywhere. Okay. Okay, this is a big picture, but I just want to explain you something. Okay, something which is for me really important, and how do I track the idea of I want a coefficiently generated category. Okay, so what I have, so first we read on the right. Okay, so I have a chain complex C. Cn is just a R module in degree n. The n of C are the cycles, so the x in C such that dx is 0. And then you have this D map, which goes from Cn to the cycles with x maps to dx. And you know that the boundary is the elements y in Cn such that there exists an x, dx equals y. Okay. The problem of there exists, and I will talk a little bit again about that, is that it's not representable. There exists, I cannot find a functor or an object that home into C will give me there exists. Okay. So for Cn, of course, we have this list, and I represented the explicit complex. R is my ring, and n at the top means that it's in degree n. So this is a complex which has only two components, R in degree n, R in degree n minus 1, and the identity within them. So a very quick check says that if you take form from this complex to C, you get back Cn. Okay, so this is Yoneda lemma. And you have this notion of spheres. And again, the complex is just concentrated in degree n, and everywhere it's 0. And then, so home from this complex to C, just the cycles. But then you cannot represent Bn of C, but you can represent the map D from Cn to the n of C, which exactly is, so I discovered that you don't see much the red things, but the red means from a complex to another complex, okay? And this, the co-kernel of this map is precisely the homology of C, okay? So you know that F has the right lifting property if and only if, well, for the first one it's surjective, and for the other one is a quasi-isomorphism. And this tells you that you have a model category structure. I mean, you have a little bit of check to prove that it's a model category structure, but very, very small check. Okay, when you have this generating cofibration and generating a cyclic cofibration. Okay, so this gives me my model category structure. On chain complex, I would like to do the same for a filtered complex. So a filtered complex is just a chain complex with a filtration. The filtration is non-decreasing or increasing, depending on, I never know which one to use. And there's a very nice description of what is the R page of the spectral sequence associated to a filtered complex. You have the R cycles, which is written here. You have the R page is the R cycle modeled by something which is the boundary, the R boundaries. But you can see it again as a map from the two copies. Ah, yes, I have this pointer. Oops. So you have one copy and you have one copy. So you can see a map from these two copies to this. And this will be representable. So representability in the context of filtered complex. So I have an explicit, it's not complex, it's filtered complex, but so now I have to explain you what are my notation here. You have a complex, so it's the same complex as for chain complexes, concentrated in degree n, concentrated in degree n-1, but it's filtered, meaning that before P, I have 0, and after P, then my R appears. And exactly here, before P minus R, I have 0, and then after P minus R, it appears. So, I mean, between P minus R plus 1 and P, you have just this thing, okay? And after you have everything goes 0, okay? So it's really nice. And indeed, it represents these cycles. So when I mean representing the home in the category of filter complex, from this filter complex to that one is precisely the R cycles, okay? And because we can send this as a map, which is kind of this thing, the boundary, okay? And the co-kernel of this map is precisely the R page of the spectral sequence, okay? And we're even able to provide, I mean, the differential from this story as embeddings of different stuff. So just, this is for your, how do you say, if you are interested, how these elements here is sent to this one. I don't know if you see very well. It just, you know, you have this thing above. You send it one copy to RP minus 1, which I'm able to do. Either it's 0, just in filtration, P minus 1. Yeah, well, it works. That's, I'm for sure. Okay, so this is to show you that in this category of filtered complex, we can do exactly like this in the category of chain complexes. And then, I mean, there's a theorem that I will explain later, well, or state later, that we do have a model category structure on filtered complex with equivalencies being the map that are quasi-isomorphism at the R page of the spectral sequence associated to the filtered complex. So now I moved a little bit to the category of multicomplex, multicomplex, filtered complex. So filtered complex, I've talked about it. I have explained you how to build this spectral sequence for a filtered complex. Now I will define this story. So in this story, it just, these two categories have the same objects. So for the operatic point of view, a very quick definition. You have maybe I write this Operad, that is a binary operad. So usually it's written R epsilon followed by epsilon squared. So just an algebra, but you can treat it as an operad, and you can take a resolution of this operad, which is exactly the category of multi-complexes if I'm taking strict morphism or twisted complexes if I'm taking infinity morphism. So I don't know what is your favorite example, but for example, A infinity algebras, you can think about strict morphism and infinity morphism between A infinity algebra. So this is the difference between multi-complex and twisted complex. So same arguments. So sometimes I call it this object multi-complex or twisted complex. It depends also because in the literature you have, I mean, this is an old notion, it's really not new, but then you have some paper where the keyword will be twisted complex and some other where the keyword will be multi-complex. And also twisted complex is not very nice because we have lots of twisting here. And well, it's not related to this thing. I mean, twisted local coefficient is not. So what is it? I mean, think about a spectral sequence, but you have all the information at first. Okay, you have this collection of ARDR. Sorry. You have this collection of graded module A, and you have a DI of pi degree minus I, 1 minus I minus 1, yeah, and well, the sum plus minus is when you compose it 0, okay? This I don't want it. Okay, and then you have the notion of morphism. So either you have a collection of maps of pi degree minus I, or you just have one map of pi degree 0, 0, which is a strict map, and it should satisfy all this equation, okay? It's better to see it as an example, and especially on the example of what I call truncated multi-complex or N multi-complex. So it's just an object like this, but di is 0 when I is greater than n. So first one, okay. When I have d1 is 0, I'm ending up with d0 square equals 0. So it's a complex, but what is important is that it's more than a complex. It's a bigraded complex. So you have all this, but at every column, okay? So for every element. So you have like columns of complexes, of homological complexes. It's what we call them vertical biocomplexes. And this category plays a very important role in the story of the Rider infinity algebras that I talked about during the introduction. N equals 2, imagine that you have your D0, D1, and it commutes, so it's what is known as a biocomplex. N equals 3, I didn't write it, but don't think that it's, chains in chains in chains. This is not this. It stops. It's okay for bicomplexes, and then it stops because you have. So I gave the example of D4, N equals 4. So I have just D0, D1, D2, D3. D0 square and D3 square are 0. So these are chain complexes. But D0, D1 commute and D3, D2 commute. But then you have this big equality, the third one, which is written, tell me that D1 square and D2 square are non-zero. So is that you don't have this thing. And so I wrote this equalities by symmetry. So you have a symmetry by changing A into n minus 1 minus A, which will play an important role later. But it gives you an idea of what would be a 4 multi-complex. Are there some questions so far? Okay. No. So now I want to talk about the functor top. So when you have a bicomplex, you know, to totalize a bicomplex into a filtered complex. So you can do that. When it's unbounded, you have to pay attention a little bit of if you choose or you pick products or direct sum. Okay. So because of the we want increasing filtration, and we are because of the degrees and so on, and I will explain you. We fix this product here on the left and the sum on the right. So it's kind of I don't know, this Laurent series, so something which is, you know, infinite on one direction but finite at the other direction. So when I explain you, I said, oh, I will put a lot of formulas, don't read them. I just want to comment them, what does it mean? So of course, this is just the space of modules involved, so bi-gradient modules or filtered modules involved. Then I need to explain the filtration. So here is the filtration by columns. Okay. But you know, I really have this is that remember that here it's not a bunches of bi-gradient modules. You have all these D0, D1, D2. And because it satisfies the condition of multicomplex, the sum of Di Dj equals 0, then the totalization, D, in some sense, is the sum of all the Di, satisfy D squared equals 0. And because of this choice of product and plus, then you're ensure that its sum is finite, okay? Because you have put a finite number of people of the form AI plus M when M goes to the infinity, okay? So this sum is finite, and you have to check, of course, that D squared equals 0, but I mean, the condition that we put on the sum of Di Dj equals 0 is just to say that D squared equals 0 when you take the sum. And here, just to satisfy that the sum is finite, and I can do that. Similarly, for a morphism. So if you have an infinity morphism, or what we call the morphism between twisted complexes, then it becomes a morphism of filtered complex. Okay? But we have much more. We have much more, and this is really, well, I love this paper because there's a lot of stuff that we have done so far. So the thing is that this category of twisted complexes is symmetric, monoidal, enriched over vertical bicomplexes. This here. The category of filtered complexes is enriched, symmetric, monoidal, enriched, and this punctured dot satisfies everything. It's enriched, lacks monoidal. So when you restrict to bounding things, it's monoidal. And also it's an isomorphism of categories when you co-restrict to its essential image, okay? It means also that, okay, you have filter complex, you don't like them very much, but just take the graded complex associated to the filter complex. If your filter complex happens to split as a direct sum of your graded components, then it comes from a unity. So that's how you recognize what we call split filtered complex, that is the essential image of system. And dot is doing everything, okay? For you. Okay, now the model category structure, I will be short on well, quick or whatever on this part. No, finally not. Sorry, I forgot. Oh yeah. Okay, so now just the survey of results. Filtered complexes, complexes, blah blah. You take weak equivalencies or ER quasi-isomorphism, meaning that when you take the spectral sequence associated to it, it's a quasi-isomorphism at the off page of the spectral sequence, and peak vibrations are those morphisms satisfying surjectivity condition. Again, you read everything on the spectral sequence or something closely. Then I should thank Sarah that I I copied her slides from from yeah, the token bone. Okay. So what we prove this thing with filtered complexes and bicomplexes. So it was in 2020, and on the truncated multicomplexes was the woman in topology 3 with Chinfu I1 in our team. Okay. Okay, but the thing is that for multicomplexes, the story is not as easy as for chain complexes and for filtered complexes. Remember that when I want to have a cofibrancy generated category, I need to have the notion of our cycles or cycles, boundaries, and something that represents it. Okay. The thing is that some sense the multicomplex is quite rigid, and the category of filtered complexes doesn't behave well with product or some, I don't remember one, but if the thing is that split filtered are not split anymore if you take some colimits or limit of split filters. So that's kind of what we're doing. Anyway, when you compute, so I explain you how to compute the spectral sequence associated to a filtered complex. I explain you how to compute the dot associated to twisted complex or multicomplex. Okay, and so I can write down directly the R page of the spectral sequence associated to a twisted complex. Okay. So I just look at ZR because this BR is, you know, something where you have a map and I don't want to spend time. But ZRPQ, so this is really, you just do the computation, okay? And you end up with this. But look at this, you have an A0 in APQ, and you say, oh, there exists some AJ, well, like this, satisfying all this, okay? So, yes, but I told you that there exists is not really nice when you want to represent it, okay? But anyway, with Sarah and Stephanie, we have with this presentation an explicit formula for the differential. It's another paper that I like very much, especially I don't cheat when I tell you I can do computation with this formula. Really. I hope that some other people can attest when I say I can do computation. Okay, but the problem is that I say this ZR are not representable. Oh, but that's not the problem. We have to find something which might be representable. So when we say there exists, we say, okay, because there is, there is. So we replace the there exists, there is by this. Instead of picking A0 and there exists A1, AR minus 1, we just look at all the R tuples satisfying the condition that we want. But no, there's no more there exists. Okay. So these R tuples are representable with no problem. Okay. We are able to produce a multi-complex such that home of this multi-complex to A is precisely this thing. And what we are lucky enough is that we have something like we can map to ZWR, and when you model by this, then you end up with what we had before. So it's another way to compute the spectral sequence of a multi-complex. It's very big, of course, but you don't have choices anymore, because that's the idea. And so now I think there's something missing. I actually have a, well, I don't know. Maybe I have a slide missing. Okay. So now what about this category of multi-complex? So now I have only strict morphism, okay? I forget about the infinity morphism. So multi-complex and truncated multi-complexes. So the thing is that, you know, I say it's unary as an opera. Algebras over the resolution of this opera, but this opera has unary operation, so it's like being algebra. And so now I'm in the category of modules over an algebra. And I know that the category of modules over an algebra is abelian. Okay, so at least I have all kernels, co-kernels, whatever I want in this category, strict morphism again. Okay. Okay, so now the screen has disappeared. What do I do? I don't know. I have not touched anything.
Mark, is the signal still coming through the screen? It is, yeah. Right, then it's the projector that's gone on the cool down cycle, most likely.
So this is the wreck.
So,
Your theorem's done. Congratulations.
so what's most likely happening is that the projector is on a cool down cycle.
I don't know, I didn't prepare all the slides to know right on the board. Sorry. I
Luckily-
protest.
Luckily, the clock has also stopped.
Yeah.
so there's no-
It'll take 5 minutes. You could continue on the joy about Belfast. I say continue on the book. It's gonna take about 5 minutes and then it'll come back on again.
Did you really want to do that? Well, I would prefer to have a break
Okay.
and then go on with my talk because, you know, I prepared it and,
Okay, great.
yeah.
Then we'll have
You're gonna give us
a
homework
4-minute
during
break.
the 5-minute break? You're gonna give us homework during the 5-minute break?
Something to think about.
If you don't mind, it just,
Yeah, no,
yeah.
it's fine. And I'm sorry it's
Because
happened
I
for
mean,
us,
on the
but
board, it's so full,
Right.
nobody sees it and.
no,
Yeah.
absolutely fine.
So Dave, you should explain what a cool down cycle is and why we got to sit through it.
Okay, then I tell you what I will do. I will go to the following. We'll do some housekeeping. So if anyone wants to go to the Titanic Museum, there are 3 complications. Firstly, getting there. That can be solved by walking or taking a taxi. Secondly, getting in there. That can be solved by paying for a ticket. And thirdly, actually having tickets available. So anyone who wants to go, they should talk to Marcy, who is running this entirely unofficial organisation.
Singing, on some of the things I will be singing the song.
But the really important point is talk to Marcy, decide if you're going to go, and then check that tickets are available, buy them in advance. Because people have turned up and they said, no, we've just got 2 coaches in off a cruise ship. Sorry, we're full. Okay, that's that.
So by you announcing this to all of us, I understand that the Newton Institute is accepting liability for any misadventures that happen.
So, Ulrika, is the Newton Institute taking liability for the excursion? Okay. Marcy volunteered.
Yeah, but you would never put me in charge of something that you're responsible.
When you're literally in charge of going to see a sinking ship. There's a walk on Wednesday, which is, I think there's less housekeeping to do. Aha! It has cooled down. And anyone who wants to ask him about the walk, ask John. I think we're back in the ready.
Yes,
Very good.
thank you for waiting. So I mean, this was, now, maybe I can move on. So we have, let's say, multi-complexes. This is, we have your bi-graded module and you have all the DI and the sum of the DI the ITJ equals 0 when I plus j is obvious. Yeah. So you can, I mean, easily see that it's just a category of multicomplexes with strict morphisms, so some of strict are just modules over a certain bi-graded ring, which is this one. So it's not truncated. So I mean, I'm taking the free ring generated by the SDI, it's non-commutative, of course, and with this. The ideal generated by this this maps. Oh, this element, sorry. Okay. You can imagine that you have a truncated version of this, just modding off that all the VIs that you don't want, or you want to be 0. Okay. So this is the first interpretation of this category. I have a second interpretation where instead of taking a ring, the bi-graded ring, I take a ring in this category of vertical bicomplexes. So I have this differential delta 0. Okay. So the idea is that, you know, when you write this thing, for instance, you have d0 dn plus dn d0 equals the sum of elements with I plus j equals n, but then they are greater than 1. Okay, you just take this, and then you externalize the differential. Okay, by taking that delta 0, you see it as a differential on the home sets and or home modules more than one set. And this gives also, so it's not modules, it's differential bi-graded module with this differential. And again, you have truncated version. So, well, to prove that it's abelian category, you don't need all that. So, I mean, you can have it restricted. But this plays an important role in some comparison of theorem. So, yes, I think I didn't have the slide where I say that I have model category structure. It does disappear. Okay. Okay, so now I can compare for two N and L, and infinity means just that I don't truncate, so it just multicomplexes. Okay. So of course I have this thing which comes from restriction, and it has a left adjoint with this induction and a right adjoint, which is co-induction. So I think that now you're very at ease with this. Okay. And not in the level of G set, but in the level of algebras over or modules over algebras. It has a left adjoint, and sorry. So this much is equivalent. So I don't know. I made something wrong about the model category structure on filtered complex and multicomplexes. So we have one where the weak equivalence has those map where ER is a quasi-isomorphism, and vibration as the one where which are surjective on page 0 to R. Okay, we have this. But so in there, we prove that this one is equivalence. Okay, so in some sense, what I'm saying is that with respect to R, looking at multicomplexes or bicomplexes is the same. The homotopy theory of bicomplexes and multicomplexes with respect to this ER. But R is fixed, and N should be greater than 2, because you see, if I'm looking at this complex, vertical complex, I do not have spectral sequence arriving with this, because I'm just taking the homology with respect to D0, and then nothing happens, okay? So by complexes, you know that if you take the homology with respect to D0 and then to D1, there is a differential in the big 2 and so on. Okay. Yeah. Sorry. The main theorem disappeared. Well, it's not a problem. I want to explain you a little result that we had recently with Joanna Sirisi, who is interested in complex geometry and precisely on almost complex structure, which really I'm not a specialist. So see it as Joanna is one of the a person who comes at us and say, oh, I need this thing as a calculation. And I say, and Sarah and I will say, oh yes, maybe let's go and try to fix something. Okay. So this is the story. So she arrived with this story about the truncated multicomplex. So when you are truncated multicomplex, you have D0, D1 up to Dn-1. So you have, because of the formula that I wrote you for n equals 4, you have an involution on the category of truncated or n multicomplexes, just by this EI, Dn-1 minus I. But then, because you have this involution, then you can take the spectral sequence with respect to A, or the spectral sequence with respect to A up. So think just about bicomplex. You can take the spectral sequence associated to the column filtration or to the row filtration. But apparently in complex geometry, it's important to compare or to have, they have quasi-isomorphism, which becomes isomorphism on the first or second page of the first spectral sequence and on the second page of the second spectral sequence. So now is there a model category structure when you can mix these two? Oh yes, so there is a theorem here, which says that we have this and write proper cofibrancy generated model structure with ERS. So what I said, it's quasi-isomorphic on the R page of the first spectral sequence and S quasi-isomorphic on the S page of the second spectral sequence. And this category, there's a model category structure with the same. It's really a mix of the model category structures that we had before. Okay, so I told you about this inclusion functor. When I have an N multicomplex, I can see it as a L multicomplex by just saying, okay, I have D0 up to Dn-1. And of course, I can put 0, 0 up to Dn-1, and I have an L multicomplex. But you see clearly that doing this, it's really not invariant under the involution, because the involution, depends on N on the first and depends on L on the second one. Okay. So, but we would like to have functors to compare these two spectral sequences, okay, this ERS. We need some functors that in some sense respect the involution, both of this category and that category. And for this, remember that I told you that I can interpret multicomplexes as modules over a ring, a bigraded ring or a differential graded ring. But the differential graded ring, you know, we make the privilege of delta 0. But then, because of the involution, why do you prefer delta 0 and not delta n-1? So this is not good. So that's why it's better to have this interpretation like this. And I want to illustrate this by considering this following case. So I have two multicomplex, I didn't say, but I think you know now that it's bicomplexes, and I have 4 multicomplexes. So what I can do, I'm taking a bicomplex, and I want to do it as a 4 multicomplex. So I put 0, D0, D1, 0, and of course you need this shift because of the, you know, the bi-degree of the differential, but there's the ways to shift the bi-degrees of A and B. But this is nice because this one comes from a map of bigraded ring from A4 to A2. And again, induction, co-induction, I have left, right adjoint to this J, okay? And we prove that this, so here we put 0, 0 and 1, 1. But in some sense, if you put RS here, you will have R plus one, S plus one. So it's just an example because it's what people are interested in almost complex geometry. So this is, we prove that it's a equivalent adjunction and they preserve the involution. So the big question is that, is it equivalent equivalence? When I say, is it a big question? So it will have an impact in complex geometry. And we tried many things. And for the present, one day we think it is, and one day we think it is not. So it's really at this stage, and we tried things. So maybe just to be short, the equivalent equivalence we proved with Agwon and Shinfu on the other model category structure, okay, works well because we had the interpretation of this as this, and we used at some point, it's not, just at some point in the proof that if you have two differential graded algebras and they are quasi-isomorphic, then the homotopy category of modules over them are homotopy equivalent, okay? When just you take the quasi-isomorphism them to be the one that are in your underlying category. Okay, so we use it at some point, but I really need to warn you that when you take the R page of the spectral sequence, as soon as you start with R equals 1, 2, then you don't have anymore like a map, a forgetful puncture to a category with weak equivalence, like chain complexes with weak equivalence, and you cannot transfer this, because this ER depends completely on all the differences you had before. Okay, I think I have time to make a short thing, and yeah, I have plenty of time indeed. To illustrate what I want, I say by this R, in some sense, is really important to go far from the homotopy theory of chain complexes. And I want to show you that the idea is that we have kind of delocalization of the homotopy theory of chain complexes with quasi-isomorphism, or maybe chain complexes with quasi-isomorphism is a localization of some model category structure we have on spectral sequences. So what I want to explain you is all the contents is in a recent paper that is on archive with Sarah. It's spectral sequences via linear pressheaves. So this is really inspired by the homotopy theory of pressheaves over a set, like developed by Royal and Cieszynski for defining infinity one categories, but in a linear setting. So maybe this just to explain you, in some sense, the techniques that are around. So extended spectral sequence, quick and simple. Okay. Think about the spectral sequence and what is the difference here? My characteristic maps are no more isomorphism. That's it. So what is an extended spectral sequence? Okay, you have a bunches of complexes and just you have a comparison map of modules between AR plus 1 and the homology of AR. In some sense, this psi R witness what happened before. You know, if you have a spectral sequence, when you want to pick an element which is in your page, your R page of the spectral sequence, it means that it comes from something. The comes from something is a psi R. So my X is sent to an element that was there in the page R minus 1. And so it's kind of, it's a witness of the representative of the homology. So to understand this very often. So, and I have this category, it's exactly the same. And of course, the spectral sequences is the full subcategory of this. So what is really, really nice with this category is that this one has all small limits and co-limits. Okay. Really a very, very nice category compared to the one of spectral sequence. So limits are computed page-wise, but co-limits is a bit tricky as they are computed via this reflector here. So I have this category LWB, and this is my what I call linear preshift, linear witness books. And in some sense, I explain you a little bit. Remember the difference between the R cycles for multicomplexes and the witness R cycle. You know, instead of there is, here I pick completely, so it's witness books. So instead of being at page R, I have my side between page R, R-1, and so on. And so I witness what there is, okay, before. So this is, and we were able to build this category as a preshift over a category of additive category, and with values in R modules. So this category is abelian. Okay. So because it's abelian, it has whatever you want. And we, in some sense, this extended spectral sequence came as a surprise when we end. So this is built from kind of disk and sphere in spectral sequence, and we kept only this, and we wonder what were the morphism between spectral sequence, and we end up with this category. But more than that, in this category, we are able to identify extended spectral sequence and spectral sequence are really nice, like objects that have a right lifting property with respect to something. Okay, so there are, how do you say, look, I don't remember the name, local objects with respect to morphism. Okay, and yeah, okay. Okay. Okay, let's go for shifted decay. So in extended spectral sequence, we have adjunctions, which are called this. It was fit to the category of spectral sequence, and it is compatible with the shift and decalage in filtered complexes. So it's a way to interpret shift and decalage at the level of spectral sequence. So that means, from a filter complex, you can build this spectral sequence, and then it's compatible with shift and decalage in filter complex.
You mean those are endofunctors? Those are endofunctors? Like
Yeah.
Because
Not really. In some sense, they are, but they are built from truncated functors.
from what?
Truncated functors. So
Okay.
it's really like when you take the truncation of simplicial sets and you have this, you say, how do you build a free simplicial set generated, or, this is exactly the same thing. But then after, when you take, the monad or the comonads, and you have your endofunctor. So here they are seen as endofunctor, but built again from truncations, different kind of truncation. Okay. Now I'm in this extended spectral sequence, so I have very nice thing. I have category which has all limits, co-limits, and then I, of course, again, is there a model category structure with but I have to choose now. Okay, my model for ER, because remember that in an extended spectral sequence, yes, I know there's 5 minutes left. Yeah. So in extended spectral sequence, there's no relation. There are these characteristic maps between the homology of one page to the other, but there are no isomorphism. So I can say, okay, I'm just taking the maps that are quasi-isomorphism at page R of my extended spectral sequence, or I'm taking the maps that are quasi-isomorphism at page R, but also I impose that there are isomorphism at every pages. Okay. So I have two choices. Okay. The thing is that both choices restrict to ER in spectral sequence, because if I am a quasi-isomorphism, on page R in a spectral sequence, then I am an isomorphism at every page after. It's a consequence of being a spectral. Okay. Never mind, both this choice have underlying model category structure, but more than underlying, like, have support the model category structure with the same hydrogens. Again, subjective, every page is below R. One is, so this one is with the R, and the prime or dash is with the ER dash, okay? So I just recall what is E dash R, so the CDR, but then you have this line. So this one, well, without a dash, is nice, but in some sense it's Quillen equivalent to the projective category of chain complexes for any R. So, okay, all this job for this, well, it's not so interesting. This thing, because we have the same vibration, and here we have more with equivalencies. So this thing is around the pseudo-localization, which is not a Quillen equivalent. So we know it. We proved that it's not a Quillen equivalent. We were able to produce an example. So that's why I say, in some sense, I see it as a delocalization of chain complexes with quasi-isomorphism. And the shift and decalage, all the model category structure here are all Quillen equivalent when V varies. It was the same in filtered complex, I didn't mention it. So now the last thing. We were interested in spectral sequence with ER, okay? So when I take E0, I think I take the 0 page, and this is a quasi-isomorphism. So isomorphism from page 1 and after. This one is homotopically full in extended spectral sequence. By homotopically full, imagine that you have a map from X to Y. One is in a spectral sequence, and it's homotopically equivalent with this E0, but then the other is a spectral sequence. Okay, because you start at E0, and then you have an I. And because it's homotopically full, so if you have a model of infinity one category, is a model of relative categories of Baruch-Kahn, and Meyer proves that when it's homotopically full of a model category structure, then it's an infinity one category in this thing. And because we have the shift and decalage that was Quillen equivalent in some sense, so it tells me that I have a vibrant replacement of spectral sequence ER in this model of Baruch-Kahn. So, well, it's nice homotopy theory of spectral sequence, and R is important in some sense, not only 0. Okay, so thank you.
That the location of SPSC was E0 is the same as the location of ESPSC is prime 0. That doesn't mean that the underlying infinity categories are the same.
Which one?
That the infinity category given by the ESP, like the ESPSC prime and SPSC E0 minus 1 are the same. I mean, I didn't understand the statement, the relative category which is homotopically full.
So homotopically full is just think about if I have I'm in extended spectral sequence here. This guy is in F sequence prime 0. This one is in spectral sequence, or the other one. Then Y is a spectral sequence. Okay.
Does it imply that the two associated?
No, it just implies that this relative category is an infinity one category, but there's no equivalence of infinity category You know, it just sometimes it happens that you have a model category structure and you have a full subcategory with has the same underlying model category structure in the sense that you have a model category structure when you restrict vibration cofibration, doesn't say that they are equivalent.
Yeah, but I'm not really asking for Boolean equivalence in this tree, like asking for equivalence of infinity categories.
Yeah, but I mean, it's the same for me in there. Yeah, the same story. I mean, yeah, it just it won't imply. It's not because it's homotopically full. You know that it's an infinity category on the nose, okay? Because the other one is a model category, and then you know, but just you have a comparison when you localize the homotopy categories from one to the other, but that's all.
It's they're different objects, right? They're
Yeah.
extended spectral sequences that aren't equivalent to spectral sequences.
Yeah, exactly.
It's not gonna give an
Yeah,
equivalent.
Yeah, okay.
yeah, it's quick and fast. Yeah,
Uh,
quick and simple.
so I hadn't heard about extended spectral sequences before, and I was wondering, do they serve a similar like computational purpose to spectral sequences, or as far as you know, it's really for the model category?
It's really for the model category structure because I mean it's really large. You know, like you cannot tell very. I mean, you can put this pi to be zero everywhere. The characteristic map to be zero, that it will work. So it's just a collection of numbers.
Does the theory of synthetic spectra somehow fit into this?
This I don't know. I have to learn what is synthetic spectrum. Yeah.
One more question.
I have a quick question. Do you have a filters like model for extended spectral sequences?
Say it again.
Do you have a filters like model for extended spectral sequences?
So for us, well, maybe it's that you just see it there. Extended spectral sequence is really nice because we see it in the word of spectral sequence. It's closely related to the notion of spectral sequence. But for me, linear witness book is the best category ever. You know, it's a abelian, and I know how to do some computation in there and so on. I know how to recognize a spectral sequence in there. That's really, really nice. And it's completely related about our witness cycles, and it was built for this.
Is this a Boolean equivalence?
In some sense, we transfer the structure, so the extended spectral sequence R, we transfer it from a model category structure on LWBR.
Yeah.
And then the one with the dash, we couldn't transfer it because this one is really closely to, I mean, we have always said something related with chain complexes. And then the dash is a transformation of this one. So the dash is not comparable with a model category structure on LW.
Oh, we should thank everybody, okay?